In our previous video, we talked about principle of virtual work, which stated that the summation over I of Fi bar dot del r I bar is equal to 0. That is correct. But that was only for the systems in equilibrium, right? Where the net force is 0. And we excluded the forces of constraints, the work done by the forces of constraint, and we wrote it as Fi bar A, right? So now what we are going to do is that we are going to see what if the system itself is not in equilibrium, right? Always it is not the case that the system will be in a translational equilibrium where the net force acting on the system will be zero. So then we have to apply something known as D'Alembert's principle. What does it say? Let us see that. Okay, suppose I have a particle, right? And it is not in a equilibrium, it is accelerating, maybe in this direction with a certain acceleration a bar, right? So that means there is a force in this direction. We'll call this as ma bar. Now, what D'Alembert's principle states is that you apply an equal and opposite force on this particular particle. Let's call this as F bar and make it to the rest, right? So then what you will get? You will get F bar is equal to minus of ma bar, right? Because ma bar is in this direction, F bar is in the opposite direction, right? And if I take the summation of these F bar plus ma bar, then obviously it is going to be 0 because both of them are having same magnitude and opposite direction, right? That means suppose you have a system of n particles and I take the ith particle like this. The ith particle force is Fi bar, then its force is obviously equal to the net external force Fi bar is equal to Pi bar dot, right? This is Pi bar dot, which is the Newton's second law. So what I am going to do now is I am going to take it towards the left, Fi bar minus Pi bar. This is going to be equal to 0 bar. Okay. Now what we are going to do? We are going to take a dot product with the virtual displacement dot delta Ri bar. But since Fi bar minus Pi bar is 0, this will be also 0, right? And if I take a summation over I, then this is what you get. And this itself is the D'Alembert's principle. Now the force Fi bar here can be again decomposed in two parts, which is the applied force, that is A, and the force due to constraint, let it be Fi bar, right? Small Fi bar. So now again I am going to write summation over I. This is Fi bar. This can be written as Fi bar A, the applied force plus small Fi bar, right? Dot del R I bar minus summation over I Pi bar dot del Ri bar is equal to 0, right? Now again the same thing, summation over I Fi bar A dot del Ri bar plus summation over I small Fi bar dot del Ri bar minus summation over I Pi bar dot del Ri bar is equal to 0. Now if you look here, this one will be taken as 0 by us because of that fact that the forces of constraints do not do any work, right? So even if you have a surface which is in under a motion, right? Suppose there is a wedge like this, and on this the particular block is kept and this wedge is moving, right? Even then this particular case we saw that the normal reaction was doing the work, right? So it was doing work only in the case of real displacements, but if you talk about virtual displacement, this particular normal reaction will not do any work if the wedge is itself moving, right? Okay, so here this will go to the 0 and hence we will write summation over I Fi bar A minus Pi bar dot dot del I bar is equal to 0, right? This is the final form of D'Alembert's principle. This is the D'Alembert's principle itself. At the some questions based on D'Alembert's principle that I will talk about in the next class.